Okay, so I think it's time to make a start. So welcome everyone to this session, which is on device independence. I'm Roger Colbeck, and I'm going to be chairing this session. As always, we've got our own Slack channel for the session, so please post any questions you have for the three talks in the Slack channel, and after all three speakers have spoken, then we'll have the questions at the end. So yeah, I think that's it. So I think we're ready to go. So our first speaker is Tony Metger from ETH Zurich, and he's going to be telling us about device-independent protocols from computational assumptions. Go ahead.
Yeah, thank you very much. So this is joint work with Rotem Arne Friedman and D'Angelo Ikkedulek and Thomas Vidic. And as you can tell from the title, we're kind of interested in basing device-independent protocols on new sets of assumptions. And in particular, we're concerned with self-testing and then mostly DIQKD. So before I tell you about this new set of assumptions, let me briefly remind you of the standard ones. So in standard DIQKD, we have Alice and Bob who want to establish some shared key, and this adversary Eve who wants to gain information about this key. And to establish their key, Alice and Bob have access to these quantum devices, which may be entangled. But crucially, these quantum devices are untrusted, which means that Alice and Bob don't want to make any assumptions about what's going on inside of these devices. Right? So then how can Alice and Bob generate a key from these devices? Well, the basic idea is that they will execute some sort of Bell test on these devices. And if they observe a Bell inequality violation, then from that, they can deduce some statement about the device's states and measurements. And from this, they can deduce that the final key, which they extract from the interaction with the device, this has information theoretic security, which means it's secure even if this adversary Eve here has infinite computational power. Now, what I want to stress is that even though this device here may be entangled with Eve and it may be entangled with the other device, there cannot be any communication across these connections. And why is that? Well, if the device could talk to Eve, it could just forward its entire interaction with Alice to Eve, and likewise for Bob. And then clearly Alice and Bob couldn't generate a secure key from this interaction. Why can't the two devices talk to each other? Well, this is really because we rely on Bell inequality violations. And for those to be meaningful, we need that these two sides are isolated. Now, what we want to do is we want to drop this non-communication assumption between these two sides. And if we do that, then the setting looks something like this, where I've drawn this in this sort of slightly funny way, because you can think of this either as just two devices connected by a quantum channel, or equivalently just as one big device that has two sort of interaction terminals. Why would we want to consider this setting? Well, from a sort of foundations or theory point of view, I think it's just kind of need to see whether we can still get information theoretic keys from something that isn't a Bell inequality violation. But more practically, you can think of this quantum channel that is now part of this device as being the channel that is usually used for entanglement distribution and actual DIQKD implementations. So in this setting, you can have this entanglement distribution channel between the two sides that is sort of permanently open, and that honest devices would use for entanglement distribution, but dishonest devices may use for whatever they want to do. And you don't have to worry about isolating these two sides from each other. So how can we generate a secure key in this setting? For this, we'll need a new assumption. And this is the assumption that this device here is computationally bounded. And in particular, it can't break a certain post-quantum cryptographic primitive. And with this new assumption, we can replace our Bell inequality violation by some interactive protocol that leverages this computational assumption. And similar protocols have also previously been considered in these works, but these are not sufficient to get DIQKD. Now, let me say a few words about this interactive protocol. So this is what we call, let me first sort of stress, because people sometimes get confused, that Eve here is still computationally unbounded. Okay, so we've introduced a computational assumption, but only on the device, not on Eve. And the final key is still information theoretically secure. So yeah, sometimes people get confused, but really we still want the same level of security as in standard DIQKD. Okay. So now let me move on quickly to this interactive protocol here. We call this computational self-testing. And the guarantee that it gives us is that if a computationally bounded device wins with high probability, then we can sort of know that the device indeed must have prepared and then measured an EPR pair. And the measurement bases are chosen by Alice and Bob in this protocol. Okay, technically, this only holds up to global changes of basis, but we can kind of ignore this. Right, so now if we move back to the previous slide, we can sort of fill in these steps. So we start from this computational self-testing protocol. We deduce that the device must have prepared and measured EPR states. And this is already kind of an information theoretically flavored statement. So once we know this, we can proceed almost as though we were in device-dependent QKD and get that the final key that we extract has information theoretic security. Okay, so that's kind of the quick outline, and you can watch the full talk for more details. Thank you.
Okay, thank you very much. So yeah, we'll take questions at the end of all the talks. So we'll move on now to Ernest Tan, who's going to tell us about finite size DIQKD with noisy pre-processing and random key measurements. So yeah, go ahead, Ernest.
Okay, so the presentation started correctly now? The slides are okay?
Yeah.
Okay, then yeah, I guess that's that. Okay, so for this talk, we are actually presenting two separate works, collaborations between quite a large number of groups, as you see on the screen here. So to give a bit of background of the idea here, so as Tony just mentioned, we are still working for this works, we are working in the standard device independent scenario. So you based on a situation where Alice and Bob perform a sort of Bell test experiment, and they check whether their devices can violate a Bell inequality. So one way we can motivate device-independent QKD is to say that if the devices violate a Bell inequality, then we can conclude there must have been some entanglement between Alice and Bob, and maybe we can use this entanglement to generate a secret key. But the important thing from the device-independent perspective is that this conclusion can be arrived at without knowing what measurements are being performed by the devices. So this is in contrast to standard QKD, where we assume the measurements are known, essentially. So the benefit offered by DIQKD is basically that we have, in some sense, a higher level of security compared to standard QKD, because in DIQKD, we don't need to trust the measurements to such an extent. And because of this, there is also improved resistance for DIQKD against some kinds of hacking attacks on QKD protocols. Not necessarily all hacking attacks, but some of them, there's improved resistance. But the drawbacks we usually face for DIQKD is that, first of all, the security analysis is more challenging, but also it has much lower noise tolerance compared to standard QKD protocols. And we have to try and overcome these challenges if we want to make DIQKD more feasible. The good news is that in the past couple of years, there were quite a number of different proposals to try and improve the noise tolerance of DIQKD. And for the time being, I'll focus on two of them, which were called noisy preprocessing, where you add a small amount of trusted noise to the device outputs, and random key measurements, which is based on using randomly selected measurements for key generation. But to give a quick overview of what is the common points between these previous results, first of all, most of them are based on the Bell inequality called the CHSH inequality. And what both of them eventually concluded is that if you only worry about the asymptotic limit of infinitely many protocol rounds, then DIQKD is theoretically possible with existing devices. For noisy preprocessing, it seems possible with photons, but for random key measurements, it's impossible with NP centers or cold atoms. But then these results, they actually raise various questions that we try to address. So one of them is, since they are based on CHSH, can we go beyond the CHSH inequality? And another question is that since these works, they studied the asymptotic limit, well, if we want to do a realistic experiment, it will only have a finite sample size, and we aim to address this with a finite size analysis. And finally, of course, a natural question, since there were these two different proposals, they were in separate works, we asked the question of whether we can combine the different proposals for improving the noise tolerance of the DIQKD. I should also mention that after we prepared this work, just within the past, I think 2 or 3 months, there were some very recent improvements as well, which I described briefly in the talk, and you can check out in the subsequent talks in this QCrypt as well. So, okay, the two works that we have here, the first work is essentially the idea we want to go beyond the CHSH inequality, and we also include noisy preprocessing as well. Should mention that, okay, there's for this particular work, there was an independent work that came at about the same time, coming out with the same result. So you should also take a look at this result as well. Then the second work that I'm presenting is where we try to combine all the different variations that I propose. That I just described rather. And we come up with an algorithm to compute the key rate for a protocol that combines all of the different variations that improve the noise tolerance. So with this algorithm, we find that you can improve the noise tolerance beyond everything that was previously known. And furthermore, we also include a finite size analysis for the protocol that includes all of these different variations. So most of the results we'll describe in more detail in the extended talk. But for example, we studied photonic models and we found that you can improve the key rates in this setting. We also studied the noise model of depolarizing noise and found, as I mentioned, higher noise tolerance for this setting as well. But when it comes to the finite size analysis, where we considered the existing bell test experiments, the results here was slightly pessimistic in the sense that if we plot the key rate as a function that can be achieved as a function of the number of rounds in the protocol, and we ask ourselves what's the minimum sample size you need to achieve a positive finite size key rate, it seems currently out of reach of the existing bell test experiments, at least for those based on NV centers and cold atoms. So yeah, to quickly sum up the contributions we are presenting here, we go beyond the CHSH inequality. We combine all the different protocol variations that were proposed in the past few years. We derive some new noise tolerance thresholds based on this, and we do a bunch of improvements to the finite size analysis. Looking forward, I just want to mention that, so based on our results, the NV center and cold atom experiments, it seems like we need significant improvement in the experimental parameters to do the DIQKD with these implementations. But on the other hand, from the results in the past few months, it actually looks like photonic implementations could be quite promising. Those results, there's still some points of the analysis which need further inspection in order to bring it all the way to a full DIQKD implementation using photons, but it does look quite promising. And this is, I think, a natural next step to carry on with this work. Also, just want to quickly mention that there's been some interest in the converse question of upper bounds on the DIQKD, but yeah, that's perhaps a separate topic that is addressed by a bunch of works recently. So yeah, this is the quick summary of what we described in the talk, and yeah, you can look at the full talk for more information. Thank you.
Okay, great. Thank you very much.
I guess I have to stop the, okay.
Yeah. Okay, and yeah, so now let's move on to the final talk, which is by Frédéric Dupuis, and he's going to tell us about privacy amplification and coupling without smoothing. Yeah, the slide is correctly.
Yeah, once you start screen sharing, it's not clear where the button is. Okay, so thank you for the introduction. And indeed, I'll talk about private simplification and decoupling without smoothing. So first of all, what am I talking about? What are these two things? So both private amplification and decoupling, the basic setting looks like this. So we have a state here, bipartite state rho AE. We think of A here as being the Alice system and E here being some sort of eavesdropper system. And then what we want to do is to take the A system, process it somehow, and get something that is uniform and independent from Eve system here. And in the case of private simplification, A is a classical system, and we're applying a hash function in order to get something that's independent from E. In the case of decoupling, then the whole thing is fully quantum, and then we apply a unitary to get a quantum system that is independent from rho E. And of course, what we want at the end is something that is close to this ideal state. And we expect an upper bound to be of this form here. So we expect something that depends on, first of all, the size of the output system. So basically the number of bits that come out of our private simplification system, or the number of qubits that come out of our decoupling. And it should depend also on the amount of uncertainty there was in A given E at the beginning here. So how much entropy we had in A given E in the state before we apply the hash function or the unitary. And there should be some sort of measure of entropy here, and which measure is not so is not obvious. I'm only going to talk about private simplification in this little talk, but my result also applies to decoupling. So what is known about private simplification? So the basic security proof gives this result. So the upper bound that we get is 2 to the 1/2 times the number of bits at the output. And here the measure of entropy here is the sandwiched Renyi entropy of order 2 of A given E. Now, if we were to use this directly in applications, it wouldn't be so good, because this H2 quantity is strictly less than what we expect. For example, for IID states, we expect the relevant quantity here to be the von Neumann entropy. So if we have the H2, that's already much less than what we should be getting. So what do we do to deal with this? Well, we use a process called smoothing. So what we do is that, first of all, we use the min entropy rather than the 2 entropy. It's better understood, and I'm not going to go into this now. But what it is basically is that we take this min entropy, which is a lower bound on the 2 entropy, and then we take the best state. We compute it on the best state in a ball centered on the state that we're interested in. And then what happens is that our upper bound turns into this, right? So we have the usual upper bound with the H min here, and then there's the size of this ball here that enters the bound. And then if we compute this over, let's say, an IID state, we get something that's close to what we expect. And I just have here the core of the proof of this fact here, the fact that the smooth min entropy is reasonably close to what we expect for an IID state, namely n times the von Neumann entropy. And the idea is that we first lower bound the smooth min entropy by the Renyi entropy, the sandwiched alpha Renyi entropy. And then in turn, we then lower bound this by the von Neumann entropy here. And in both of these steps here, we incur a penalty cost here. And then to get the bound, what we do is that alpha here is some parameter that we can choose, and we choose alpha to be 1 plus something very, very small, like order of 1 over square root of n. And this trick doesn't only work for IID states. In particular, it works for states that arise in the entropy accumulation theorem. So, for example, like in security proofs for DIQKD, if you use the entropy accumulation theorem, then at the core of it, there's essentially this proof going on as well. And one thing you might ask when you see this sort of proof is, well, maybe there's a way to cut out this min entropy entirely, like get rid of the smoothing. And basically, what if we could just have a proof like Renner's proof, so for H2, but instead of having H2, we'd have H alpha for any alpha above 1. Like if we could just have it directly for the alpha that we choose here, something that's close to 1, then we could just cut out this entirely and have a proof that only works with Renyi entropy. And this is the result that I'm presenting here. So the main result is essentially an upper bound of the same type that as Renyi's as Renner's proof rather, but where the upper bound here, instead of having the 2 Renyi entropy here, you have any alpha between 1 and 2 here. So in particular, you can pick an alpha that's just above 1 and not have to worry about smoothing anymore. And then the score of the proof gets replaced by something much simpler here. And then if you optimize over alpha, you can easily get an error exponent for the task you're interested in. So you get something that's tighter and much simpler as well. And if you combine this main result with entropy accumulation, and so I'm not going to go into exactly what this is, but this is basically the sort of state that comes out of let's say DIQKD, for example, like A1 to AN would be like the raw key. T1 to Tn would be like, did we win the ith CHSH game in our protocol? then if we apply our main theorem to this, then we get a nice error exponent for the whole task here. And in particular, for those of you who are into this sort of proofs, in the original EAT approach, we had to assume something about the let's say the number of CHSH games that we won overall. Like you had to assume that the adversary didn't have something that won with a that the statistics you see are not something that's too improbable somehow. You had to make an assumption over this. And if you use this proof instead, then you have something that enters the expression in a way that you don't have to care about it. Basically, it enters in a much more natural way. You can ask me questions about this point if you're interested. About 2 words in terms of the proof idea. Basically, what you can do is there's something called the Ristorin interpolation theorem that lets you interpolate between two Schatten P norms. And the idea is that you can write H alpha as an alpha norm, and then you basically use the same sort of techniques as in Ristorin to interpolate between alpha equals 2, which is Brenner's original result, and at alpha equals 1. All you have to do is use a trivial bound of 2 on the 1 norm on the left hand side of the expression. And then once you do this, the interpolated version is essentially the main theorem. Finally, let me conclude with a few open problems. So one question I'm interested in is, can we do this with basically all of one-shot quantum information theory? Like, can we reunify all of it? And another interesting question is, this should allow us to get rid of something called the simultaneous smoothing problem in multi-user information theory. So a lot of problems in quantum multi-user information theory involve multiple terms that have a smooth min entropy or a smooth max entropy and so on, all of these smoothed quantity. And when you have many of them arising in your problem, often what you want is to have one state that achieves all of the that's good for all of the smoothing problems involved. And if you use this to get rid of smoothing, well, you get rid of the problem entirely because you just don't have smoothing anymore. So with that, I'd like to conclude my talk. Thank you.
Okay, thank you very much. So that completes the 3 talks for this session. So now we have time for questions. So please post them in the Slack channel for this session. There aren't any there at the moment, but let me quickly ask Fred while we're just thinking about his talk. So you present, the way you present this just now is more as a kind of nice theoretical tool. How much tighter does this enable us to make, for example, device-independent security proofs, if at all?
Right. So, well, one thing it does is that you can actually get a better error exponent. Like if you if you look at the expression you're going to get at the end on the right hand side of the, like you're going to have your security statement, and then you're going to have your bound on the right hand side here. You can actually show that the exponent you're going to get here as a function of n is actually going to be higher than anything you can get using smoothing.
So you're not sharing a slide anymore, are you?
Oh, good point.
Just when you say here.
Yes, that's a very good point. Yeah, so this is what I was trying to show. So yeah, if you have your security statement here on the left, you have your bound on the right here. So and then you have some exponent here that's going to be a function of n in any QKD scenario, and then you can show that the exponent you're going to get, so it's going to be 2 to the something times n. It's actually going to be higher for using this technique than the other one. And this is actually worked out in a paper by Hayashi. I can give you pointers to it if you're interested. No, I haven't done any actual numerics when it comes to having a concrete protocol. But yeah, okay. I'd be interested.
It would be expected to be better, but that's hasn't been done yet.
Right.
Okay. Okay, thanks. So let me just look. So we've got Okay, let's have a question for Ernest. So how does the nature of the systems, cold atoms versus NV centers versus photons, enter into the analysis of the DIQKD protocol?
Right. It's just in terms of defining the honest behavior of the protocol. So in the sense that, yeah, there's always a bit of a trade-off in a certain sense, but like you can prove the security of a protocol. For example, you can quite easily prove security of a protocol that only accepts if the CHSH value is above like 2.8 or something. But then the question is, do you have a device that can actually do this? And so when I talked about the anti-center and cold atoms, it's just the question of what DIQKD protocols could they realistically implement. Yeah, so it's in terms of characterizing the honest behavior.
So do you mean it's just only about the value of the inequality, or is there something more than that?
Right. For the particular protocol we did the security proof of here, it's just the value of CHSH they can achieve and the QBER, so to speak, for the error correction term, which is not necessarily coupled as simply as the depolarizing noise model, but for these setups, yeah, we can treat them as separate parameters and do the calculation based on that. Yeah.
Okay, but that doesn't seem to actually make use of the exact nature of those systems. So I guess you're only using knowledge about how well those systems can behave in terms of achieving CHSH violations.
Right. So I guess I should, I should clarify in that case. What I meant was in terms of what we currently understand to be the current experimental performance achievable by these experiments. Yes. Yeah.
Okay. Right. Thanks.
Okay. Thank you. We have another question for Frederick. Do you know some interpretation or operational meaning for the parameter alpha? For instance, the smoothing parameter in smooth entropy can be seen as a failure probability in a certain task. Can we understand alpha in a similar way?
I don't think I have an equally compelling operational interpretation of the parameter itself. Right? Also, for the smoothing parameter, you could it's sort of it's true only on a very high level. If you really look at the epsilon as the purified distance, you have to convert to another distance before we can make that interpretation, for example. And yeah, the alpha parameter, I'm not sure I have a really good interpretation of it. It's a good question.
Okay, so there's food for thought for the audience members. Okay, let me just ask one question for Tony. So when you make this assumption that, or you're trying to drop this assumption that the two devices cannot talk to each other. Now, if you're doing something like QKD, and you say that there's this channel and we allow it to do everything, then of course that channel between the two devices would normally be assumed to pass via an eavesdropper as well. But if you do something like, for example, randomness expansion, then both Alice and Bob will be in the same lab. And so there, in that case, that dropping of assumption might be more reasonable. So does what you do basically carry over to randomness generation pretty much as one might expect, or are there any extra difficulties there?
Yeah, I think it does, though it's sort of slightly pointless in the sense that we already had protocols for randomness expansion in this computational setting before. So this is one of these references that I cited by Berkowski and others who kind of did this. I mean, the idea for having this for QKD is that you're kind of, I mean, if you actually want to implement this in practice, which whether or not you want to, we can discuss separately, but if you actually do, then the sort of scenario that we have in mind is that you're in a setting where you're kind of reasonably confident that this locality assumption holds entirely. So you're reasonably confident that you've isolated your devices from Eve and also from each other. But then you've got this quantum channel between the two sides kind of lying around, which you don't have to Eve, right? You only have it between the two sides. So this might sort of give you some pause as to whether these two sides are really isolated. So then you could plot this computational stuff on, sort of on top if this is a remaining security concern. But the idea is that you still, I mean, you should start from a place where you have sort of some reasonable confidence in having isolated these devices, because otherwise they also could just talk to Eve, and this we clearly can't account for.
Yeah, okay. Yeah, I think it's maybe a little bit difficult to sort of make this cut between the devices can talk to each other down this channel, but not to Eve. So I totally agree that we need to make sure that they cannot talk to Eve. But
it means it's somewhat awkward asymmetry, I agree. So I guess like the justification is that you do in the honest implementation, like there is talking going on at sort of between the protocols, between the devices, but not between Eve. So there is sort of some level of asymmetry in the implementation already. Whether or not this is sufficient to justify it, I guess, depends a bit on what the actual implementation is and what security concerns you still have.
Yeah, I mean, in principle, if you trust the security of that link, you could just send your message down that link without the key.
True, right. So this is why I said then the whole thing would be pointless, right? So yes. This is why I said you sort of want to be, like you hope to be in the standard setting, but you have this remaining bit of uncertainty. But it's not a sort of clear-cut thing. It's more of a,
yeah, sure.
If this is what concerns you, then here's a solution for it.
Okay, thanks. And we just have, I think, a couple more questions for Frederic. So in your work, you use strongly 2 universal hash functions. Does your version of the leftover hashing lemma work for any 2 universal hash functions? I guess they want to remove the strongly.
Yeah, so that's I'm going to update the paper soon, and yeah, it does work for 2 universal hash functions.
Okay, thanks. That's a quick answer. And one more. So this is maybe a bit specific on slide 7, which I guess most of the audience don't remember which was slide 7 now. But you briefly mentioned that some assumptions from the original EAT paper could be relaxed. Could you elaborate on that? So maybe you can share the slide again, just so the audience know what's being referred to.
You're muted.
You're on mute, Fred.
Okay, sorry about that. Okay, can you hear me?
Yeah.
Okay, good. Yeah, so this was the slide in question. The idea is that when you're proving security using of a DIQKD protocol using the entropy accumulation theorem, you have to assume a bound on the winning, like the probability of seeing what you see. Essentially, like you have to assume that the probability that, let's say, the adversary won I don't know 88% of the CHSH games. You have to assume that probability is, let's say, at least a certain number. Like the probability of seeing this shows up in the bound on the right hand side, right? And so you have to make some sort of assumption on it to be able to have a concrete bound. What this does is it brings it on this side of the equation in a way that you don't really have to care about it, right? Because then you're basically weighing your security, like your security statement here, by the probability of seeing this. So then you can sum over all of the possible events, like the probability of seeing a certain value times this one norm here, and then you can sum over all possibilities, right? Like I could sum over W here, and at the end I get a nice security statement where it never enters the bound on the right hand side. Like in this sense, it enters the bound in a much more natural way, in a way that you don't have to care about it. You don't have to make any assumptions on it.
Sorry, maybe to jump in a little and phrase it slightly differently. I will not exactly say that we assume the probability is bounded, but we do a case analysis. Let's say you do, you do one case where it's bounded, and you do one case where it's the other side of the bound, and you prove them separately, which I admit is a little annoying in the security proof. Yes. Yeah.
No, exactly. No,
I think your audio, is it me or is your audio?
Right, like you have to choose this line, this cutoff somewhere, and do it. Okay, it's probably me again. Hello.
Yeah. Okay. I think we just caught the answer. You broke up a little bit, but I don't know. For me, I was able to understand the answer after a little delay. Okay, I think we're out of time now, but all the speakers will be available in the Meet the Speakers area, I believe. So if you have any further questions or want to discuss anything with them, you can just head over there. So thanks to all the speakers, and there's a poster session that will be the next thing beginning, I think, in 10 minutes time. Other than that, we'll finish there. Thank you.
Oh, although Frederick, Tony, could we just quickly find you in the speaker lounge for a little bit? I had a question I wanted to check, but thanks.
Sure, I'll be there.